Welcome to University Utara Malaysia's cryptography module, led by Dr. Ala Jabbar Al-Maliki. We often assume that if data is hidden from prying eyes, it is safe. Today, we are going to test that assumption. We need to ask a specific question. What happens if hiding data is not enough to actually secure it? This diagram displays the 4 core security services in cryptography. While previous sessions covered confidentiality, protecting the secrecy of data, we are going to isolate and examine integrity and authentication. A common misconception is that secrecy guarantees integrity. Notice this encrypted data packet moving across the network. Because it is encrypted, an outside observer cannot read the contents. However, an attacker does not need to read a message to alterate. Watch the interceptor node. The attacker blindly scrambles the bits of the encrypted packet and sends it along. When the legitimate receiver decrypts the message, a standard transfer of 100 ringgit has been corrupted into a transfer of 900 ringgit. Relying solely on encryption leaves a massive structural gap in any communication system. To build a secure protocol, the system must mathematically prove that the data arrived exactly as it was sent and that it came from a legitimate source. This visual contrasts the two mechanisms. Encryption acts like a heavy steel safe. It keeps unauthorized people out. Authentication acts like a tamper-proof seal. It provides proof of the message's origin and confirms it remains entirely intact. To create that digital seal, systems use a message authentication code, or MAC. We start with the original message and a secret key. We feed both into a specific MAC algorithm, which generates a small piece of data called an authentication tag. By requiring a secret key, the tag is permanently tied to the specific sender. When the message reaches its destination, the receiver takes the incoming text and their own copy of the exact same secret key. They run the calculation themselves. If the receiver's new tag perfectly matches the tag attached to the message, the system verifies the match. Because only the sender and receiver possess the secret key, a matching MAC proves the sender's identity and the data's integrity. The system works perfectly, provided the two parties have a secure way to share the key. Let's look at the underlying math. This diagram shows a hash function. It takes an input of any size, a single word or an entire textbook, and mathematically compresses it into a fixed-size string of characters. This output is a digital fingerprint, unique to the exact data provided. This process relies on the avalanche effect. We input the word hello in all caps and generate a specific fingerprint. If we change the capital O to a lowercase o, the resulting fingerprint completely scrambles. Even the smallest modification produces a wildly different output. But consider a scenario where we only use plain hashes without a secret key. An attacker intercepts the data, deletes the original message, and writes a fake one. Because hash functions are public math, the attacker simply computes a brand new fingerprint for the fake message and sends them both to the receiver. To stop an attacker from generating fake fingerprints, modern protocols use HMAC, a hash-based message authentication code. By looking at this formula, we can see how it integrates secret keys directly into the hashing process. We can break this complex equation into 2 logical steps. First, the inner layer takes the message and wraps it with a modified version of the secret key, then hashes it. Second, the outer layer takes that resulting fingerprint, wraps it with the secret key again, and hashes the entire package a second time. The message is mathematically bound to the secret key twice over. An attacker who intercepts the data cannot compute a new, valid fingerprint because they do not possess the required key. Let's consolidate these concepts. This decision matrix compares encryption, plain hashes, and MACs across our core security requirements. Encryption provides confidentiality and is reversible. Hashes provide integrity, but they are entirely irreversible. MACs deliver both integrity and authentication, but offer zero confidentiality. In practice, these tools are combined. A secure HTTPS web session uses HMACs for authentication and encryption for secrecy. VPNs use similar pairings to secure remote tunnels, while blockchain relies heavily on secure hash algorithms like SHA-256 to build immutable public ledgers. Hashes are particularly critical for password storage. When you log into a university portal, the database does not store your plain text password.
It stores the one-way hash. If the database is compromised, the attackers extract irreversible fingerprints, keeping the original password secure. For your upcoming tutorial with Dr. Al-Maliki, review the end-of-chapter discussion questions. Remember that robust cybersecurity requires combining secrecy with unforgeable integrity. Without a mechanism to verify who sent the data and that it arrived unaltered, even the strongest encryption leaves the system vulnerable.